Hey guys, just making a quick video here to continue our work with inequalities. So we will be solving an inequality in class, and very similar to solving equations. There's really just one rule that we want to be careful of. And we're also going to recap what that looks like when we graph it on a number line. So we're really covering a lot of learning targets at once here, but I know you guys can handle it. We are solving a one-step, two-step, and a multi-step inequality, right? So just like we solved all of those equations, we're going to do it all with inequalities. And we can represent the solution to an inequality on a number line because we're not getting just one answer anymore, right? Now we're getting multiple answers. We have everything that's less than one number or greater than another number. So your symbols that we have to look at are the less than or equal to, and we have the greater than and greater than or equal to. And so the equal to represents us including the value that is that we get as a solution. So we're including that number as part of the solution. Whereas just a less than or a greater than tells us that we just want everything that is either less than the number we got as an answer or greater than the number we got as an answer. Still gives us an infinite amount of possible answers, possible solutions. But we at least have something to compare it to. So we use these symbols to compare. So when graphing with a less than or a greater than, you would use an open circle. And if we use our interval notation, that would be a soft bracket for those types of symbols. If we see an equal to, that's when you're going to have the closed circle on the number line, or what we call a hard bracket on our number line or in our interval notation as well. Okay, so let's jump right in here and try an example. So you want to follow all the same steps you would follow as if you were solving an equation. And then when we get down to the end, we'll talk about the couple of things we have to be careful of. So my first step, right, is to clear the grouping. So clear the parentheses by distributing. So 3x minus 2x, and then negative 2 times negative 1 is positive 2. So when you distribute, remember taking that whole piece with it, is less than or equal to 5. Now we want to combine like terms on the same side if possible. So here I see 3x minus 2x. That gives me 1x plus 2 is less than or equal to 5. Now I can combine like terms from the opposite sides. So take away 2. So x is less than or equal to 3. Notice I didn't write 1x anymore because 1x and x are the same thing. Okay. And now we just have to think about how to represent the solution. So this is saying that my answers to this problem are any x values that are less than or equal to 3. So that could be 2.9, could be 0, could be negative 100. Any single number that is less than or equal to 3 would be part of this solution. So we have 3 ways to write it. Set notation. We can use the set brace and say we have all the x's such that x is less than or equal to 3. We could write it as an interval, which we'll look at in a second, but first let's put it on a number line. This is the most common way to represent an inequality. Whenever you're making your own number line, sorry, that was not straight, but whenever you're making your own number line, I want you to have at least 3 numbers. So put the number that you got when you solved, and then one number greater than that and one number less than that. So I would do 2 and 4. Okay. So once we get that, we can circle the 3, and if it's less than or equal to 3, we're including 3 as part of our solution. So I'm going to fill in that circle to show I'm including 3. And then this sign, as long as my variable's on the left, should point the direction we want to shade. So I want everything less than or equal to 3, so everything to the left. And that's really going all the way back to negative infinity, right? So if we're going to write it in interval notation, that would tell me I'm going from negative infinity up to 3. I'm never including infinity, right, because it's a destination, so soft bracket there, hard bracket on 3 because I am including that number. And you could alternatively do that on your number line. So if we had 3, 2, 4, that was poorly spaced. We could say, okay, we have 3, and then we have everything to the left of that. You can use the bracket instead of the circle. Means the same thing, okay? So that's our first example there. Solve it just like you normally would. It's just the way we represent the solution that's different. Let's try example 2. So here, there's no parentheses to get rid of, so I want to start by combining like terms. I'm always personally going to try and move my variable to the left. It's easier to read the inequality that way. If you move it to the right, that's also fine, but then you have to remember to flip it at the end, okay? So I'm going to start by taking 8z and moving that to the left by doing the opposite, which is subtracting. So negative 2z plus 7 is greater than negative 7. And then to get z by itself, now I need to move the plus 7 to the right because we want to get rid of our addition or subtraction first. Those cancel, so negative 2z is greater than negative 14. And then the last step would be dividing by negative 2. So we end up with z and positive 7. And when you divide by a negative with an inequality, what a negative really says is to negate or make the opposite of your statement, okay? So what we have to also do is take our inequality sign from being a greater than and switch it to be a less than, all right? So make a nice note of that in your notes when multiplying or dividing, which is what we did here, but it could be multiplying as well, by a negative number, switch the inequality sign. All right, so that is your golden rule here for solving inequalities. That's the most important thing to remember. And this tells us that we have all the values z that are less than 7 as part of our solution. You can check it by picking any number that is less than 7. So maybe 0 is less than 7. So let's say z is equal to 0. If I put that back in my original equation, we have 6 times 0 plus 7 is greater than 8 times 0 plus, minus 7. Well, 6 times 0 is 0, so we get 7 is greater than 8 times 0 is 0, negative 7. This is true, right? So if it's a true statement when you're done, then I know I got the right answer, okay? So we could say here, if I wanted set notation, all numbers z such that z is less than 7, or if I put it on a number line, I'm going to mark 7, 8, and 6. And then when I go to graph it, I'm going to circle 7. And we have to ask ourselves, is 7 included as part of the solution set? So 7, because it's just the numbers less than 7, not less than or equal to, we're not including it. So we just want everything less than 7, which would be shading everything to the left. All right, all the way down to negative infinity. Alternatively, we could write from negative infinity to 7, both with soft brackets because we're not including those values. All right. Or again, if we had another number line, so many ways you can represent this. At 7, we could have just the parenthesis there and then everything shaded to the left, okay? All right, now let's look at a special case. So example 3, 3w plus 24 is greater than 3 times w plus 8. Let's start by solving it just like we normally would, so get rid of the parentheses by distributing. So 3w plus 24 is greater than 3w plus 24. If you remember, when we had an equal sign there, if it was exactly the same on both sides, we had an infinite solution or identity situation here, okay? In this particular case, though, we have an inequality, so things are going to change a little bit. So let's try and solve it and then see what we end up with. So I'm going to take away 3w from both sides. So 24 is greater than 24. Is this true? Is 24 greater than 24? No, right? So if it's a false statement, that would tell us that there's no solution. So there is no number we could substitute in for w that would ever make this inequality true, right? We could try when w is 0. We get 0 plus 24 is greater than 0 plus 24. Again, 24 is greater than 24. Nope, that doesn't work, right? So it doesn't matter what number w is, if it's always the same and both sides are actually equal, one will never be greater than the other. Let's see how that changes when we have 3w plus 24 is greater than or equal to 3w plus 8. Well, again, here I go with my distributing. So 3w plus 24 is greater than or equal to 3w plus 24. If I subtract 3w, just like we did, we get 24 is greater than or equal to 24. Well, that statement, greater than or equal to, is always true, right? 24 is always equal to 24. So that's a true statement. So this is where you have infinite solutions, or you could say all real numbers as your solution, right? Whenever this is true, we have all real numbers. If it's false, then we have no solution, okay? So let's look at one more iteration of this. Let me get a different color here. Again, 3w plus 24 less than, and so I'm going to distribute here, 3 times w and 3 times 8. So 3w plus 24 is less than 3w plus 24 minus 4. Now let's try and solve. So I'm going to combine like terms on the same side. So 3w plus 24 is less than 3w plus 20. Take away 3w from both sides. 24 is less than 20. Is that true? No, 24 is never going to be less than 20, so this is a no solution situation, right? If I asked you, okay, what do you need to change to make this all real numbers instead of no solution, what do you think that might be? Well, if this symbol was just going the opposite direction, 24 is greater than 20, then that's something that's always true, right? 24 is always greater than 20, so that would be all real numbers if we did something like that. But the way it stands right now is no solution.